You probably know terms like white dwarf, neutron star, supernova, red giant, etc. Especially if you are interested in astrology, you have heard these names, which are apparently used to refer to different types of stars, depict the different realities of a star's life. Stars are born, grow, and finally die, a cycle that can last between a few 100 million years and a few billion years. Therefore, millions or billions of years should be spent to study the life cycle of stars from their birth to their death. Since humans do not have such time, and the process of changes of a star is very slow compared to the life of a human, by studying different stars and examining them, scientists arrived at the stellar evolution model. The evolution of a star, which represents the life cycle of a star, is a process that a star goes through during its lifetime and takes different times depending on the star's mass. There are more than 10 trillion billion stars in about 100 billion galaxies in the universe. All stars are born in massive molecular clouds, giant masses made of gas and dust floating in interstellar space. Stars form when these molecular clouds, also known as stellar nurseries, undergo gravitational collapse. Gravitational pressures cause the temperature of the nebula to rise and break it up into smaller clouds. These clouds are each a protostar, the mass that forms the primordial nucleus of a star. A protostar is a ball-like object that is in the early stages of becoming a star. The protostar has an irregular shape and contains both gas and dust. The protostellar stage in a star's life cycle can last several hundreds of thousands of years. Gravitational effects cause the gaseous core of the protostar to start rotating. In an effort to reach hydrostatic equilibrium, the protostar is contracted. Its brightness decreases and its temperature remains constant, and at the end of this path, a star is born. As the star is born, the nuclear activities that are its beating heart begin. It is the energy released during this process that makes the star shine. During this time, the star slowly feeds on its hydrogen and makes helium through nuclear fusion. When the hydrogen runs out, the star's life story enters a new phase that depends on the initial mass of the star, a path that may lead to a massive explosion or end with the star cooling and fading. Life cycle of low-mass stars. Low-mass stars include a group of stars whose mass is less than 8 times the mass of the Sun and is considered a red or yellow main sequence star. This category of stars includes 95% of all stars in the universe. After the star has burned almost all of its hydrogen, its core begins to contract and heat up, causing the hydrogen to burn even faster. This extra energy created radiates outward and causes the outer layers of the star to move away from its core. As the outer layers of the star expand, they cool and become redder and redder, and the star enters the red giant phase. The red giant stage is the third stage in the life of low-mass stars. At this point, the star's core has become hot enough to begin burning helium, a nuclear fusion process in which heavier helium nuclei join together to form larger nuclei such as carbon and then oxygen. Burning helium as the star's new fuel source takes a few thousand to a billion years, but eventually the helium in the core will run out, and after most of the core has been converted into carbon and oxygen atoms, the star will have no more fuel to burn. As the last helium particles are burned, the outer layers of the star are separated and spread back into the interstellar space. The ejected shell of the star forms a mass known as planetary nebula. The material in these nebulae is reflowed into the interstellar medium to join with other existing gas and dust particles to trigger the formation of another star. As the planetary nebula separates, a small, very hot, bare core of the star remains, a body called white dwarf. White dwarfs are the last stage in the life cycle of low-mass stars because these stars do not have enough mass to become a supernova. White dwarfs have Earth-sized volumes, but they are very dense and their mass is about the mass of the Sun. Despite this, and compared to larger stars, a white dwarf is considered a cold and dim star due to its lack of energy. When the star turns into a white dwarf, the end of the star's life comes. In the process of star decay, there is another hypothetical stage after the white dwarf stage, which is known as black dwarf, when the star has cooled enough that it no longer emits any heat or light. Since the time required for a white dwarf to reach this stage is thought to be longer than the current lifetime of the universe, no black dwarfs are expected to exist in the universe at present. Even if black dwarfs exist, they are difficult to locate due to the lack of radiation. Life cycle of massive stars. This category includes stars with more than 8 times the mass of the Sun. Although the formation and beginning of the life of this group of stars, until the stage of burning hydrogen, is similar to low-mass stars, they choose a completely different path of life, which makes their death not very slow and silent. Due to the higher initial mass, the gravitational force, and thus the inward pressure, is much stronger in these stars, resulting in a hotter star. The higher temperature causes the nuclear fusion process to occur more rapidly, which counteracts the effect of the higher gravity of these stars by producing more outward pressure. As a result, when these stars are born, we see a star that is big, hot, and blue. The difference between the life stories of high-mass and low-mass stars is keyed from this point. While low-mass stars take billions of years to burn through their fuel, massive stars burn through their fuel in much less time, consuming all their hydrogen in just a few tens to a few 100 million years. As with low-mass stars, as the hydrogen fuel runs out, the core of this group of stars begins to contract and heat up, which causes the star to inflate and produce more energy. As a result, we are faced with a star with very large dimensions called supergiant, the rarest stars in the universe that can be tens of times brighter than the Sun and have a radius 1,000 times that of the Sun. At the same time that the core of massive stars condenses, its temperature becomes much higher compared to low-mass stars, and as a result, it can produce elements of carbon, oxygen, neon, and silicon by fusion of helium nuclei. These elements gather in order of gravity in smaller and smaller regions toward the star's center that are hot enough to trigger their special fusion process. Finally, in the center of the star, we encounter the heaviest element that can be formed during the interstellar fusion reaction: iron. After all, the nuclear reactions in the different layers are done, and the fuel runs out. A star with an all-iron core is left behind, which means the death of the supergiant star. The iron core is so stable that nuclear fusion is no longer able to create new matter and produce energy, and as a result, upon reaching this stage, gravity wins and the star's core collapses in a fraction of a second. During an explosion, a huge release of energy takes place, and the dust and gases of the star's outer layer are thrown into space at a speed equal to 30,000 kilometers per second. This extraordinary event, which is one of the most violent and energetic events in the universe, is called a supernova. These explosions, while causing the creation of elements heavier than iron in the periodic table, create such a glow that its light alone is greater than the light of the entire galaxy in which the supernova is located. Unlike low-mass stars, supernovae do not leave behind a white dwarf. Since the remaining core of these stars has a mass more than 1.5 times the mass of the Sun, the amount known as Chandrasekhar limit, the gravitational force of the core can overcome the pressure of electron decay. In this case, two things happen. If the mass of the nucleus is between 1.4 and 3 times the mass of the Sun, the nucleus cannot resist gravity, and when the electrons collide with protons, only neutrons remain. The result is a neutron star whose entire mass is concentrated in a sphere with a diameter of less than 20 km. But if the mass of the core is more than 3 times the mass of the Sun, gravity is even able to overcome the neutron decay pressure. As a result, all the mass of the star is concentrated in a single point with infinite density, a kind of singularity that we know as black hole. Therefore, although it may seem impossible, but nature works in exactly the same way, and black holes are actually the last stage of life of the most massive stars in the universe. Now you say in the comments whether the Sun is a red giant or a supergiant. If you like this video, support us by liking and subscribing so that we can produce more videos about this.